Hi class, welcome to your third lecture in chapter 22, the acid-base chemistry of carbonyl compounds. As I always state, it's highly encouraged to go back and look at the previous video lectures from this chapter before continuing on this lecture. But today will be a short lecture where we apply the knowledge we've learned about enolate chemistry towards reactions. Everything is given by God. All talent, creativity, ability, insight, and strength comes from Him. In our own strength, we can do nothing. That's a quote by Marvin J. Ashton, and that has served as our chapter theme. So here's what we've done this far. We've talked about acid-base reactions focusing on carbonyl-containing compounds, aka how ketones, alpha carbons, protons are relatively acidic when, for instance, compared to alkenes and alkanes. We also have discussed why ketones have higher acidity than alkanes, as I just mentioned, and we introduced to you this concept of enol ketotautomerism and how it's applied to isomerization reactions, such as the carbonyl transposition and racemization reactions, which I used a little case study on a drug called thalidomide, where it racemized the drug. Understand how to predict which enolate ion will be formed when unsymmetrical ketones are used, and so that's when we entered into our discussion of thermodynamic versus kinetic enolates, be it LDA, lithium diisopropyl amide, versus KH, potassium hydride. And you can go back and look at those video lectures to see which one, LDA or KH, will yield the kinetic or thermodynamic product. Make a note that both of these reactions are done in THF, so we are not talking about an aqueous environment for those particular enolates. Today we're going to learn halogenation reactions of enolate ions, and then the reactions using enolate ions will spill over into chapter 23, where we learn the aldol reactions. Halogenation at the alpha position. So this far we've only talked about general information about enolate ions and tautomerism. Here's what tautomerism is. It can result in racemization. I did give you a carbonyl transposition reaction of carbohydrates. And we've talked about, the mechanisms of generating enolates in acid or base environment. Remember that the acidic environment went through actually an enol intermediate, not an enolate ion. But the point is that you have this keto-enol tautomerism that can happen. And then I also talked about, how to form enolates using LDA or KH in an organic solvent such as THF. That's interesting and all about how to form them, just like it's interesting to discover how to form organolithiums or Grignards or Gilman reagents. But the question is how do we use these towards organic synthesis? And so that's what we're talking about here. And as I mentioned, it'll spill over into chapter 23. As it turns out, enolate ions in related species, they're nucleophilic, meaning that they do the attacking towards electrophiles. And this section, as we conclude this chapter, will focus specifically on chlorine, bromine, and iodine reactions, so halogenation reactions. Okay, so let's just quickly recap what an enolate ion might look like. Okay, so that would be the enolate ion, and if you were to protonate this would be called the enol form, aka a vinyl alcohol. And bear in mind that this has a resonance structure in which you could draw the ketone. So this is called the keto form, which is actually the more stable of the two because you have that carbonyl bond and the nucleophilic carb anion. So that's what we're going to be talking about here in particular, is this nucleophilic center right there at that alpha carbon. So here is reactions of enolate ions and halogens. It's a mechanism in aqueous environments. So note that this is aqueous, this is not LDA and THF. And so this first reaction right here, as we start the mechanism, should not surprise you. You take cyclohexanone or any other ketone, and you can deprotonate it in the alpha position using a strong base. In this case, we're looking at the hydroxide anion, which is the conjugate base of water. What happens is it would deprotonate at the position that's alpha to a carbonyl group. Recall that that's alpha, and that might be beta, and that might be gamma. And then once you deprotonate, you form water from the hydroxide, and the electrons will go on to form a CC double bond, okay, to give you the enolate ion. There you have it, the enolate ion. And Quickly, that oxyanion collapses down to make a stable carbonyl bond. But then those electrons that just formed the CC double bond, aka the alkene portion of the enolate, goes on to react, okay? And so those electrons are going to be very nucleophilic, and if it helps you, you may want to think of this as a carbanion, okay? And what do you know about carbanions? They do the attacking, okay? And so that's all what's going on here. As those electrons collapse down from your oxygen, the electrons from your CC double bond, the pi bond in particular, need to go, and they're going to react with something. They're going to find the bromine in this reaction. Keep in mind, I'm showing you the basic environment mechanism, so I'm going to go over the acidic environment in a few slides. Now you may say, why is it attacking bromine? Bromine looks like it's nonpolar, and you are right, bromine is nonpolar, Br, Br. They both have equal distribution of electrons. It is nonpolar. It tugs that direction. Is in the same magnitude. It tugs in the opposite direction, causing them to be nonpolar. But do not forget about dispersion or van der Waals forces or London forces, however you might have learned how to say them. It's an intermolecular force that's seen in every single molecule. So as this Br2 is floating around in solution, at any instantaneous moment in time, that bromine might possess a partial positive and that one a partial negative, and vice versa, and it's going back and forth, back and forth, back and forth. But at any instantaneous moment in time, you might see one of the bromines having a partial positive, and it's going to be balanced with a partial negative. Now, if that's true, that can govern, or at least rationalize, the pattern of this reactivity. So if these electrons from this enolate ion and the CC double bond are reaching out, that must mean that that bromine in particular has a partial positive and that one a partial negative at that moment in time, the way it's drawn. Now, you may recall that halogens like one bond in order to be neutral. So you have to kick off the other bromine in order to make everything happy, if you will. Okay, so what we did is we successfully brominated in the alpha position. You're going to see we're going to stop at this point in the acidic environment, but now that we're in the basic environment, we're going to continue on. There's some reasons behind it, and I'll discuss those further when we get to the acid-based, not base, but the acid mechanism. But I do want to point out this particular statement right here. This proton now is more acidic than it was before in the original ketone, okay? It's now more acidic. Why? Because of the inductive effect. You now are not only alpha to a carbonyl group, which is, has a resonance structure, and you have some electron withdrawing qualities about it. You also are attached to a carbon that bears a bromine, and bromine is relatively electronegative, okay? Remember, electronegativity goes right there, and then bromine is a halogen, and it is just below fluorine and then chlorine, and then you have bromine right there. So it's pretty electronegative because it's up here in the top right corner, which means that that particular proton that I just circled right here is relatively acidic because it has resonance structure on the left side and some electron pull on the left side due to electronegativity, and it's also on a carbon attached to a bromine, making it further further acidic. It'll stabilize that carb anion because it's going to tug those electrons in various directions. And remember the theory that the conjugate base is more stable, the better you can pull electron density over a larger area. Okay, so that's all what's going on there. It's helping to stabilize the conjugate base. And now this proton's more acidic than before, so then this reaction is going to happen again. In order to finish you off, you pluck off that particular proton. You've seen this mechanism because it's the same as steps 1 and 2 until you get the dibromo species in that particular position. Now, I've never done this reaction. I can't say I've read about it that much. I do want you to learn it because I think there's patterns that you need to know, and it kind of introduces you to enolate ion reactivity. But I do want to mention that I imagine that this reaction would have a lot of practical laboratory issues. The question is what if you added so much bromine that it attacks right there? So you're going to want to control the amount of bromine that you're adding to the reaction very carefully, okay? Because who's to say it won't go there if you have excess, okay? And then you're just going to brominate this molecule in 3-4 different ways, And so I just see some practical issues, but some key traits of just the simple use whatever ketone you may have, and you react it with a base and some halogen. That Br2 could have been an I2 or a Cl2, not an F2. Okay, you don't do this with fluorine. It's just too electronegative and not reactive enough to participate in these reactions. So, as always, we stick to Br, I, and Cl. Just know that for all available alpha protons, you're going to react in the alpha position and replace each proton with a halogen. In this case, it's bromine. Here's an actual named reaction, so it's a subset of the one I just demonstrated to you using the base in an aqueous environment, but this one is called the haloform reaction, so you may know that CHCl3 is called chloroform, CHBr3 would be called bromoform, and CHI3 is called iodoform. This might help you remember that this is called the haloform reaction because in this particular reaction, these are the types of products you form, CH and then X3 or 3 halogens, if you will. And the other byproduct would be like a carboxylate anion, as I just made note of right here on the slide. Of course, under acidic conditions, that's going to be protonated to the carboxylic acid. But what you need to know about the haloform reaction, as I said, it's a subset of the one that I just talked about, is that you need to start with a ketone that has a methyl group attached to it. That's the main trait of this one. Notice I have a ketone, and this is just any R group. Okay, that can be whatever. But you need to have a CH3 on the other side to engage in the haloform reaction. And so let's take a look at the reaction conditions. You want excess X2, which is just Br2, Cl2, or I2, and a base in this case because we're dealing with aqueous environment. The strong base we typically like to use in aqueous environments would be the hydroxide anion, being OH minus. As I previously mentioned, you need to use a methyl ketone, and you transform it to a carboxylate anion having one less carbon atom. Okay, so where if you look at the actual reaction conditions where I just boxed, that CH3 becomes an O minus. Okay, and that boxed CH3 becomes CHX3, just to kind of keep track of what is going on. And so let's take a look at that reaction mechanism in the next slide. Here's the haloform reaction mechanism. Keep in mind that that's just nothing more than an R group on the left side of your carbonyl group, and you need that CH3 methyl ketone. At that point, you know I'm going to be forming a a haloform of some sort. Bromoform, iodoform, chloroform, whatever it may be. And so you go back a couple slides, you can see how this type of mechanism works, but we have OH minus and an I2, and so essentially all what you're going to do is, like I said, just like a couple slides ago, that OH is going to pluck that off. You're going to form the enolate ion, and then once you form the enolate, that's going to collapse back down, and the double bond is going to go and hit that I2 to give you a mono-iodo compound in the alpha position. And so go back a couple slides, see if you can understand how this process works, because what's going to happen is we're going to do it again and again to get the tri-iodo compound in the alpha position with respect to the carbonyl group in the ketone. Once you have the Ci3, and by the way, this is, see those 3 stars I put right here? That's the reason why it required excess halogen, because you need enough to do it 3 different times. Okay, so in the actual reaction conditions, it called for excess. This is the reason why. Okay, now that you have your Ci3 on the right side in this particular molecule, what's going to happen now is your hydroxide does not act as a base anymore. Okay, so you may notice in the top, the hydroxide's acting as a base where it's deprotonating in the alpha position to the ketone or the carbonyl group in every step. Bases accept protons, remember? Well, now hydroxide decides to change its role a little bit, and instead of acting like a base, it's going to act like a nucleophile. And so you've seen this in many types of chemistries and organic too. You've seen it in the Grignard reaction where a nucleophile attacks the carbonyl group. You saw it in organolithium chemistry where a nucleophile attacks the carbonyl group, and you saw it in the imine, hydrazone, oxime chemistry. You saw it in enamine chemistry. You've seen it time and time again, and even the Wittig reaction. And so I just wanted to let you know this shouldn't be an unfamiliar reaction because the carbonyl group has a partial positive here and a partial negative. So nucleophiles will be attracted to that carbon there in the carbonyl group. So hydroxide acts like a nucleophile, attacks that central carbon of the carbonyl group, giving you this tetrahedral sp3 hybridized intermediate, which then collapses down, and it has 3 options. It can kick off an R group, it can kick off an OH, or it can kick off the Ci3, and it chooses actually to kick off the Ci3, which may look a little bit weird. And the reason it looks a little bit weird is because we know that you're not going to lose an R group because that's a carbon, right? And we said carbons make terrible leaving groups. They're strong bases. Strong bases are not good leaving groups. And we know that we're not going to lose hydroxide very easy because we talked about how OH is not a good leaving group. But you may argue OH minus is already in the reaction. It would make a great leaving group. And I would agree with you. It looks like it would be a great candidate. But as it turns out, Ci3 is the best leaving group on this molecule because what you have is a carb anion. But recall that you can stabilize this anion by having electronegative groups attached to it. So that carb anion is split and being pulled in 3 different directions as a stabilizing effect. Therefore, it can actually be stable on its own. This is one example where carbon is a good leaving group only because it has stabilizing groups surrounding it. Okay, just like the inductive effect, how that resulting minus charge where you deprotonate something next to a ketone is it's okay on its own. It's pretty stable. Well, for the same reason, and that's the inductive effect, especially like if you have an F right here or an NO2, for the same reason, this particular leaving group with 3 iodines on it is going to be okay because iodine's relatively electronegative. Go back and look at the periodic table and notice that it is. And also, we all know that carboxylic acids are good structures as well, stable atom arrangement. And so, yes, you just formed a carboxylic acid. That's great. You formed a Ci3 minus. That's great. It's stabilized through induction by 3 iodo groups. Keep in mind, had those been 3 electron donating groups, this would not happen. Okay, remember, electron withdrawing groups help stabilize carb anions or negative charges. Electron donating groups disrupt the stability. To finish off this reaction, that particular leaving group, though I just claimed that it's happy, it's not overly happy. It does want the full octet on that, not the full octet, but it doesn't want to charge if it can help it. And so what it's going to do is it is going to deprotonate the carboxylic acid, recall pKa of about 5, so that is relatively acidic. The carbon is happy. It acts like a base. It rips it off from the carboxylic acid. You're left with a carboxylate anion. You know that that is going to be more stable than a C with a minus charge. Why? Because the carboxylate anion has resonance structures, so it's relatively stable, and also a negative charge on an oxygen is better than a negative charge on a carbon because oxygen is more electronegative, therefore wants electrons around it more so than carbon ever does. So what you end up getting is your carboxylate and iodoform in this case. Please send me email questions if this was unclear to you, but I did my best to explain it and articulate this in a way that hopefully you understood. And here is the last reaction for this chapter. It's halogenation of enolate ions in acidic media. So what we have, again, just like our basic reaction a few slides prior to this one, is we had cyclohexanone. And recall that this is just going to be like the formation of an enolate, but not really an enolate. I do want to be very, very clear because you never form an enolate using acidic media in aqueous environments. Instead, you go through an enol. And if you were to examine right now this particular mechanism, you'll notice there's not an enolate ion on here. This is an enol because that's the one seen in the acid mechanisms. So, nonetheless, if you recall the acid mechanism, what happens first is you protonate the carbonyl oxygen to form the oxonium ion, which is right here. And then you can think of that as an activation, okay? Think of that as an activation in order to even make those alpha carbon protons more acidic than they already were. Okay, why? Because now that your oxygen has a positive charge, it wants electrons even more because oxygen does not like to have a positive charge. Oxygen likes to be negative. Okay, so if it can gain electrons, it's going to be happy. These alpha protons are more than happy to leave. So that's what happens. Water acts as base, deprotonates, you form your enol intermediate. Remember, enols aren't very stable. You might also call these vinyl alcohols. You have acid. That enol collapses down the electrons from the CC double bond in the alkene. The pi bond reaches out, nucleophilically attacks the Br2. Remember, this is like a dispersion forces, and so that would be a positive, that would be a negative at that instantaneous moment, the way I have it drawn, resulting in this particular oxonium ion with a Br in the alpha position, and then water goes on to deprotonate the oxonium ion to yield the ketone with an alpha bromo with a net increase of H3O plus. in this reaction. Okay, and so why is only the monohalogenated product formed? Well, not to get too complicated on you, the monohalogenated product is formed over the polyhalogenated product as we saw in the basic environment, because whenever you enolize this in acid, meaning you're making the enol, actually you're not making the enolate, it's slower than whenever you make an enolate ion proper with like an O minus. And so just because of the simple rates, this one doesn't go very fast. It's not going to sit there and multi-halogenate this or polyhalogenate this, just because generation of that is a lot slower. Okay, so it's just a rate argument. Well, class, that concludes this particular lecture. I hope that you enjoyed it. I hope it made sense. Please go back and watch it. It was a short lecture. So practice, practice, practice. Here's what I'm going to leave you with as a chapter ending life lesson from the Proverbs in chapter 16, verse 3. Commit your work to the Lord and your plans will be established. So just have resolve to finish this semester well as we go on to chapter 23, our final chapter in this course.